These are slides that were presented 9 years ago, December 2013. I'm presenting them again because they supplement the book Faster Than Forecast, the story that ice tells about abrupt climate change. These are the first results from the Dark Snow Project. And as you can see from the title, the presentation examines the role of black carbon, darkening of the Greenland ice sheet. The topic of microbial abundance in the darkening of the ice sheet is also touched upon. This, as you can see from the author list, was a collaborative effort that I'll touch on, thanking these people along the way. The Dark Snow Project originated during the record warm 2012 summer when my home state of Colorado was on fire and I was on my way up to Greenland. And the idea about this smoke being one of the darkening factors was an unanswered question in 2012. And so I got it in my mind to make the science happen to examine this one effect. At the same time, I had been looking at satellite measurements of the reflectivity of the Greenland ice sheet, and especially comparing the early part of the record here, 2000, with the record warm year, 2012, there was a substantial darkening of the Greenland ice sheet. So again, what role did black carbon play in this story at that time was an open question. What I had just published just weeks before the record melting in Greenland in 2012 examined the albedo feedback, that is, an initial perturbation of darkening from heating can lead to more sunlight absorption and more melting. And part of the story, important part, was persistent atmospheric circulation changes. So on the right side, you see how the last years of 2007 to 2011, there was a more of a high pressure system prevailing over Greenland, which had more of a south air movement of relatively warm air onto the ice sheet. So the warm air movement plus the high pressure that is typical of this so-called ridge pattern, it produces this kind of circulation which is associated with clear skies. So clear sky conditions plus the pumping of relatively warm air from the south was part of the melt increase story of 2007 to 2011 as compared to this earlier baseline. But there was still this question of what is the darkening effect of black carbon and potentially microbial factors. That study became concentrated on this area here that's been called since 1996 the dark zone. And this is where, for every degree of warming, that's Kelvin degrees, there is this summertime average increase of 18 watts per square meter. So this actually adds up to a lot more melting, provided that the temperature is elevated. So this was a measurement of albedo feedback. And part of this story, it has to do with the metamorphic effects, where a fresh snow crystal has more angular edges, and melting rounds those edges, so there's less scattering, less reflection, more sunlight absorption. So there's a metamorphic dimension to the albedo feedback that this presentation explores further. Yeah, the bare ice exposure. Again, down here, this is where the seasonal snow cover melts off completely, and you get a darker bare ice exposure. So there's a lot of so-called light absorbing impurities on this bare ice. And what we now know is that has a lot to do with microbial activity. And anyway, this study really focuses more on the snow albedo feedback. So wildfire is occurring not only in Colorado, but across the Arctic. And these are major uncontrolled burns, releasing, as you can see, plenty of smoke into the atmosphere. And in fact, during our 2013 expedition, Mackenzie got this photo showing a smoky sky. And it was confirmed also to be fire indeed happening to the west over Canada. Also confirmed that field workers on this date up at a place called Dai 2 on the ice sheet, they saw a red sky. This is a signature of a smoke-filled atmosphere. So indeed, smoke was arriving to Greenland, and as I had found 1 year earlier and presented this at the AGU meeting, so now 10 years ago, instances where this laser in space is able to profile the atmosphere and return um, what we confirmed was indeed smoke reaching Greenland and possibly contacting with the surface. We looked at backward trajectories of atmospheric flow, and you can find instances when a source region, a fire somewhere here in North America can connect to Greenland. The Dark Snow Project ran for several years. It ended up with quite a lean budget as compared to some of the much larger projects that were funded subsequently. So we could do little, but through largely volunteer efforts from here, Joe Immons' uh, graphic design skills were put to this idea to illustrate this hypothesis, wildfire soot reaching Greenland, which of course led to the idea, well, what about industrial soot, black carbon? And these images were shared widely and imprinted in the public mind this idea how much pollution could be darkening Greenland. Bill McKibben helped us get the word out by suggesting in our crowdfunding videos that the public help us make this research happen. This was unconventional style of funding to actually put your scientific ideas out into the public. And these were legitimate science questions. You had the right formula to attract funding. And so we did. It wasn't a lot of funding, but it was enough to make an expedition. So by the summer of 2013, just, well, 1 year after the first idea for the Dark Snow Project, we were in Greenland. We were accompanied by a Rolling Stone journalist, Jeff Goodell, who published a massive piece entitled Greenland Melting um, that attracted quite a lot more visibility to the Dark Snow Project. We were partnering with ice microbiologist Marek Stibal and working with communicators to, like Jeff, to document what we were doing, to again get that out into the public. So here's a map of the albedo, or the darkness of the Greenland ice sheet. So these kind of brown colors here, the dark brown is between 75 and 77% of the sunlight is reflected. In North Greenland, that reflectivity it reaches its peak according to these satellite measurements. And here at one of our targets, the southern topographical divide of the Greenland ice sheet, a place I called in 1997 Saddle, because it's shaped like a saddle on a horse. You have South Dome here and Summit to the north. This was our target. You can see the reflectivity here is quite high. It's say 69, 66% reflectivity. This is typically a dry snow area. It's not melting. We also took samples in areas where there is a lot of melting. Lower down on the ice sheet, it's warmer. Melting happens a lot sooner. Yeah, these were the 3 sample locations from our 2013 expedition. Locations really kind of chosen based on the information from the satellite measurements of the reflectivity. So there we were. It took a lot of resourcefulness to bring a helicopter all the way to the ice sheet southern topographical divide, this place we called Saddle. Here is the Saddle automatic weather station that I had installed in 1997. Returning to this site more than a decade later, was a powerful feeling. The equipment still running even today, 2022. I'm with the Geological Survey of Denmark and Greenland, and we are still maintaining these measurements. So we have a long record here. But our purpose that day, with just 1.5 hours on the ground, was to obtain snow cores. And from these, one core would be used to sample black carbon. Mackenzie Skiles here did that black carbon sampling back at NASA JPL later that year. She was digging a snow pit to also take some samples for black carbon and to make contact spectroscopy reflectance measurements that could give the grain size on the pit wall. It was cold and windy. The work was difficult, and I remember Mackenzie got kind of snowed in this pit with drift. Um, but she managed to get black carbon samples, as I also managed to get 2 cores. Yeah, that second core was for the ice microbial cell counts. So we were successful at this site, even though it was not good conditions and the time pressure on site was not good. As you can see, this is pretty high in elevation, 2,450 meters. This is something like 8,000 feet above sea level. And in a polar environment, we had minus 15 Celsius plus some wind, which made it, kind of like frostbite conditions. And just an hour and a half on ground, it was really tough. The black carbon sample results showed that indeed during the 2012 summer, there was elevated black carbon. So this confirmed black carbon reaching the Greenland surface in a wide layer here. That's what 20 centimeters had this occurrence of black carbon. These concentrations are not extremely high. You need concentrations up above 60 to get melting happening easily. Um, and that's really interesting. And that's where I'll go further with these relatively low black carbon concentrations. Um, can they produce melt? what has been shown in other studies, this from Greenland, if I remember correctly, just higher concentrations. This is typical that over time, especially as the surface can melt, actually the light absorbing impurities, they can concentrate on the surface. This has been called scavenging. And so that's an important point, that over time, provided that the black carbon isn't continuously buried with fresh snowfall, there can be elevated black carbon right on the surface, which would absorb quite a lot more sunlight than if the black carbon were below the surface. Yes, this is a location from Greenland where the effective light absorbing impurities got very high in summer 2009, according to this study. So, uh, indeed, black carbon can reach levels at the surface of the Greenland ice sheet that are well above any kind of threshold needed to push that surface into melting. Um, I took the data that we had and using a calculation, looked at the albedo difference for different concentrations of black carbon. So at a concentration of 0, there's no difference between the clean and the black carbon loaded albedo. And as you add black carbon, the albedo at a concentration of 20 nanograms per gram or parts per billion, same, will reduce albedo by almost 1%. So only a 1% reduction is what we would expect for the black carbon concentrations that we observed from Saddle in 2013 of the 2012 uh, melt layer. Yeah, I'm going. Okay, I'm using this Danish Meteorological Institute's implementation of an atmospheric, well, weather forecasting system under the name HIRHAM 5. This is a high resolution model, even by today's standards, 10 years later. So it was a real pleasure to work with these data, which resolve detailed features of Greenland. I'm using also this network of automatic weather stations and the Greenland Climate Network automatic weather stations that I personally installed in the 90s. Um, Now that I'm with the Geological Survey of Denmark, I'm also helping maintain PROMICE stations. So here we have a network of automatic weather stations that provide constraint or a check on this weather forecast system. How accurate is it? And the field observations are the gray line. This is 1 year, 2012, of air temperature from the lower, middle, and upper can stations that you saw in the previous slide. And the agreement between the models is quite good. These biases are really low. This is to confirm that the HIRHAM data are useful. Similarly, with downward shortwave, this is sunlight. The intensity of sunlight in, actually, these should be watts per square meter, um, matched closely. You can see that the observations are slightly higher than in the model. Otherwise, the um, day-to-day variations are quite similar. So, okay, well, with this bias, there's actually more energy for driving surface heating from black carbon than the models are giving. The long wave, this is the infrared radiation coming down from the sky. important because it's a heating factor. It's not as large as you can see. Let's go all the way up to the upper elevations. You've got about maximum 300 watts of thermal infrared coming down. And if I go back, it's there's more energy from sunlight. So here is uh, the surface energy budget. The net infrared radiation is the downward infrared minus the surface emission, which is a strong function of the surface temperature. The net shortwave is the downward incident sunlight minus the reflected energy. So 1 minus the reflectivity is the um, the upward. So this would be actually would be S down times the reflectivity would be the net shortwave. The surface energy budget is the sum of these radiative fluxes uh, balanced by the sensible, latent, and conductive energy fluxes. Okay, so all of this energy at the surface, uh, I'm relating to changes in albedo via a, a fitting parameter B and Z. So when the surface energy budget exceeds zero, the surface is heating. And I'm using albedo, which is observed from satellite observations, and I'm fitting a model so that I can get the change in albedo with the change in temperature. These are the parameter that came out of this fitting. Um, and this is my calculated surface energy budget residual. When this is positive, the surface is heating. When the residual is negative, the surface is cooling. This can drive melt. This can drive freezing or cooling of the surface. The tuning, 2 slides before, produces this uh, result or this fitting that matches the observation. So I'm tuning that function you saw before against the observations. The blue is the satellite observations of the reflectivity at this location, can M. The gray lines are the observations from the ground station. So there was good agreement between the ground and the satellite observations, and even with the function that I fit to the data. So not surprising, really. And now there's a perturbation. If I lower the albedo by 1% over time, you can see there's just this tiny or this small 1% difference. Um, what this doesn't show is how the energy that's absorbed by the surface would increase uh, due to this darkening perturbation. The darkening perturbation is as if there was a coating of black carbon on the surface of 20 nanograms per gram, sufficient to darken the surface by 1%. And that's the perturbation that I'm going to show you in the following. Um, what because the albedo change was linked with the surface energy budget, the initial perturbation grows because of that metamorphic heating that I built into this function. So it when the albedo is reduced, the the energy budget is more positive, and through these these coefficients, the change in albedo with time can um, run away, and that is this modeled effect. That the initial perturbation of just a 1% albedo drop grows through feedback more than a factor of 5. the so here is uh, an animation of this parameterized albedo according to that function that I showed already. So, and I'll run this one more time. The You start out with a bright surface around zero point 0.8, and you get a darkening because of the increase in absorbed sunlight. You saw the how the fitting of that worked at this place can M down here. And here the metamorphic heating similarly produces a darkening at the saddle where it's relatively warm. And on this date, the 23rd of June, around the summer solstice, here you can see the difference of unperturbed and perturbed. The perturbed having that 1% initial albedo decrease, unperturbed, perturbed. You can see that there is a darkening in the perturbed, and it's actually more than a constant offset of 1. And that is more clearly illustrated when you run this, the difference of the perturbation and the non-perturbed over time. And as this runs, and this is without the addition of new fresh snow to darken the surface, in some areas up here, you have this factor of 5 additional darkening across the southern ice sheet in the year 2012. Um, the so the difference with the constant or the initial perturbation of 1%, it grows over time. And this is the albedo feedback. This demonstrates how the impact of even a modest 1% decrease in albedo, it is felt when the impact can integrate the heating over time. And this is the point that so far I haven't seen in publications, and I have failed to publish this work. This is part of why I'm presenting this uh, now alongside the book, which goes into yet more detail of the Dark Snow Project. Chapter 7 in the book tells the full story of the Dark Snow Project and how it got also involved in the ice microbial question. Um, Here's another way of looking at this over a full year. Um, the Greenland ice sheet is cooling in the early season. This is normal. The net radiation at the surface is negative, so the surface is losing a lot of exijoules of energy. Now the surface starts heating up again when the sunlight turns on in the summer heating season, and this extra energy is what drives melt. The 1% perturbation initially started here grows through feedback so that the peak energy, cumulative energy of the Greenland ice sheet peaks at a value that is 40% higher uh, with this darkening perturbation of just 1%. So this sensitivity study demonstrates this cumulative effect of this initial perturbation. In reality, there will be some summer snowfall which will reduce the this effect. So this is exaggerated because this is a hypothetical summer where you don't have any snow. But 2012 was like that. It had this high pressure which kept the surface from accumulating much snow. Um, this initial 1% albedo perturbation grows for the ice sheet to more than a factor of 2, to a more than 2% perturbation. So this sensitivity study, I think, really demonstrated a lot. So in conclusion, um, surface energy budget surplus and background albedo offer a reasonable approximation of albedo versus time. This initial perturbation, it grows from 1%, you could make it 2%, Um, Fresh snow precipitation would mask this effect, and any additional black carbon would further amplify this effect. So you have this competition between brightening of the surface and darkening of the surface. Uh, this crowd-funded project obtained samples that provide the means to separate the contributions of snow and ice darkening uh, between its metamorphic time integrated effects and its instantaneous effects. And yeah, this was a milestone in the darkening of snow kind of science. There's only a handful of scientists globally that are working on this question. This Subsequently in 2018 and was it 2017, some studies came out kind of downplaying the effect of black carbon uh, and saying, well, only when black carbon is extremely high, like 60 parts per billion, do you get a clear melt signal. And I think what those studies kind of missed was this time integrated effect. So thanks for your attention, and check out the book at sila.cool, sila.cool. Sila means climate. Sila.cool is the site where the book is available in many chapters. Some of them are free, others you pay for the chapter, and along with that, you get trees planted in Greenland by me. Um, so thanks for your attention, and have an ice day.